Hello, Matt here from ChemistryStudent.com. In this video, we're going to look at the nucleophilic substitution reaction between a halogenoalkane and ammonia, forming an amine. We're going to talk about why and how these reactions happen, outline the reaction mechanism, and look at how primary, secondary, and tertiary amines can be formed in such reactions. Other reactions and mechanisms of halogenoalkanes have been covered in separate videos. Check the links in the description below. Before we talk in detail about the reaction, there are a few essential ideas you need to be comfortable with. Halogenoalkanes, also called haloalkanes, are a group of compounds that contain an alkyl group, carbon and hydrogen chain, bonded to a halogen, fluorine, chlorine, bromine, or iodine. In simple terms, they are like an alkane where a halogen has taken the place of a hydrogen. Amines are a group of compounds that contain an alkyl group bonded to a nitrogen that is itself bonded to hydrogens or further alkyl chains. They are derivatives of ammonia, meaning they come from ammonia, NH3. Amines can be primary, secondary, or tertiary. A primary amine has an NH2 group at the end of a carbon chain. The nitrogen is bonded to one carbon atom. A secondary amine has an NHR group. The nitrogen is bonded to two carbon atoms. A tertiary amine has no hydrogens bonded to the nitrogen. The nitrogen is bonded to three carbon atoms. Quaternary amines can exist as positively charged ions. Apart from with iodine, the carbon-halogen bond in a halogenoalkane is polar due to the halogen's high electronegativity and carbon's low electronegativity. This means the halogen pulls the electrons in the bond towards itself slightly and as a result has a partial negative charge, and the carbon it is bonded to ends up with a partial positive charge. As halogen size increases down group 7 in the periodic table, from fluorine to iodine, the covalent bonds they make to carbon get longer and therefore weaker. This means a carbon-fluorine bond is very strong and has a very low reactivity. A carbon-iodine bond is however weaker and more easily broken, making iodoalkanes much more reactive. A nucleophile is an electron pair donor that is attracted to a positively charged or electron-deficient atom. Nucleophiles can be negatively charged and always have a lone pair of electrons. A substitution reaction is where one group or atom in a molecule is swapped for another group. Bases are species that can accept H+ ions. In organic chemistry, we showed the possible steps occurring in a reaction by using mechanisms. Curly arrows are used to show how a pair of electrons move as bonds get broken and formed. The arrowheads always point towards where the electron pair is moving to. Recap done? Let's go. Halogenoalkanes can react with ammonia in ethanol to form an amine. The reaction is an example of nucleophilic substitution. A molecule of ammonia, NH3, is able to act as a nucleophile as the nitrogen in the molecule has a lone pair of electrons that allow it to form a bond to an electron-deficient atom. The carbon atom bonded to a halogen in a halogenoalkane has a partial positive charge, and this makes it vulnerable to attack by nucleophiles, nucleophilic attack. When a halogenoalkane is mixed with ammonia, the nitrogen in the ammonia gets attracted to this partially positive carbon and forms a bond to it. At the same time, the carbon-halogen bond will break with the bonding electron pair going to the halogen, releasing a halide ion. The nitrogen in the ammonia group bonded to the carbon now has too many bonds, 4, and as a result has a positive charge. To stabilize this intermediate, a surrounding ammonia molecule will act as a base and accept a H+ ion from the positively charged nitrogen group, itself becoming a positively charged ammonium ion, NH4+. As the nitrogen-hydrogen bond breaks, an electron pair goes to the nitrogen and it loses its positive charge, becoming neutral. All this leaves an NH2 group bonded to the carbon chain of the original halogenoalkane, a primary amine. An ammonium halide salt is formed from the positively charged ammonium ion and negatively charged halide ion. It can be tricky to see why the nitrogen ends up with a positive charge in the middle of this mechanism. Inside a carbon-halogen bond, the halogen and carbon each share one negatively charged electron. You can kind of think of it as one electron belongs to the halogen and one to the carbon. As the carbon-halogen bond breaks then, the halogen effectively takes back its own electron and the electron that belongs to the carbon atom as well. This means the carbon atom loses one of its electrons as the carbon-halogen bond breaks. The nitrogen forming a new bond to the carbon uses its lone pair of electrons, and as the bond gets made, the carbon kind of takes one of these shared electrons for itself. The nitrogen can be thought of as losing an electron here, and as a result ends up with a positive charge. The same idea is true for an NH bond to the positively charged nitrogen. One electron in the bond belongs to the hydrogen and one to the nitrogen. As an NH bond breaks and a H+ ion is lost, the nitrogen takes both of the electrons for itself, effectively gaining the electron that belonged to the hydrogen before, and this cancels out the positive charge of the nitrogen. The species starting this reaction, ammonia, acts as a nucleophile, making the reaction nucleophilic, and an amine, NH2 group, has been substituted for the halogen in the molecule, making the reaction a substitution reaction. This is why the reaction and mechanism is described as nucleophilic substitution. There are actually two ways this reaction can occur, depending on the type of halogenoalkane reacting, and they are referred to as SN1 and SN2 reaction pathways. The examples shown in this video are SN2 as primary halogenoalkanes are used. For an SN1 mechanism, the carbon-halogen bond has to break before the nucleophile, in this case ammonia, can form a bond to the carbon. SN1 and SN2 mechanisms have been covered fully in a separate video. Check the links in the description below. Now, a key property of amines is their ability to act as bases, because the nitrogen in the NH2 group has a lone pair of electrons and can accept a H+ ion. Due to the positive inductive effect of the alkyl chain in the amine molecule, amines are very good bases and readily accept H+ ions. The positive inductive effect and basicity of amines has been covered in much more detail in a separate video. Check the links in the description below. The lone pair of electrons in the nitrogen in an amine also means, however, they can act as nucleophiles. If the concentration of ammonia in the reaction mixture is low, it is likely that a primary amine already produced in the reaction earlier on will end up reacting with another unreacted halogenoalkane molecule. In this case, a secondary amine gets produced. The primary amine produced earlier in the reaction acts as a nucleophile, and the nitrogen in the NH2 group uses its lone pair of electrons to form a bond with the partially positive carbon in the halogenoalkane molecule, just like ammonia did. The mechanism now proceeds as previously shown. The only difference is, rather than a molecule of ammonia taking the H+ ion from the intermediate, another primary amine will, and as a result, one of the products of the reaction would be an alkyl ammonium halide salt. This can be repeated again with a reaction between the secondary amine just produced and another unreacted halogenoalkane molecule. Now a tertiary amine gets formed. It is even possible for a tertiary amine to act as a nucleophile and react with another halogenoalkane molecule, now forming a quaternary ammonium ion. As the nitrogen no longer has a hydrogen bonded to it, it can't lose a H+ ion and become neutral, meaning it remains as a charged ion. For any of these substitution reactions to occur, the ammonia has to be dissolved in ethanol. This is described as ethanolic conditions, and it means no water is present. If the ammonia was dissolved in water, so aqueous conditions, an alcohol would form instead. Heat is also required, and due to the high volatility of ammonia, the reaction vessel and container must be sealed to prevent any gas escaping. Let's have a quick recap of this reaction and mechanism using bromoethane and ammonia as an example. A molecule of ammonia comes close to the carbon-bromine bond in bromoethane. The nitrogen has a lone pair of electrons and is able to act as a nucleophile. It uses its lone pair of electrons to make a new bond to the partially positive carbon atom that is bonded to the bromine. At the same time, the carbon-bromine bond breaks and the bonding pair of electrons goes to the bromine, forming a negatively charged bromide ion. An intermediate is formed with the nitrogen that bonded to the carbon having a positive charge, as it has one too many bonds. Another ammonia molecule acts as a base and takes a H+ ion away from the nitrogen, leaving a neutral NH2 group behind. The product formed is an amine and has the name ethylamine. Ethyl because the alkyl group has 2 carbons in, and amine as a type of molecule formed is an amine. The ammonia that accepted a H+ ion becomes an ammonium ion, meaning ammonium bromide is also formed, made up of the positively charged ammonium ion and a negatively charged bromide ion released in the reaction. Further substitutions can occur, and ethylamine molecules already formed can act as a base and remove H+ ions from new intermediates formed in the reaction, producing ethyl ammonium ions and leading to the formation of ethyl ammonium bromide salt. Ethylamine molecules can also act as nucleophiles and react with more bromoethane to form a secondary amine, diethylamine. The diethylamine could then react with more bromoethane to form a tertiary amine, triethylamine. Finally, it is possible for triethylamine to act as a nucleophile and react with bromoethane, if there is still any left, to form a quaternary ammonium ion, tetraethylammonium. This charged ion would pair up with bromide ions already released and form the salt tetraethylammonium bromide. In these substitution reactions, the carbon-halogen bond must break before the amine can be made. The easier it is to break the carbon-halogen bond, the faster the amine can be formed. Due to the size of halogen atoms increasing as you go down group 7, carbon-halogen bond length also increases, and this makes the bonds weaker. Carbon-fluorine bonds are the strongest and carbon-iodine bonds are the weakest. So, to summarize, halogenoalkanes can react with ammonia in substitution reactions to form amines. The reaction must be carried out in ethanolic conditions. No water can be present, and this is to stop an alcohol from forming. The reaction is an example of nucleophilic substitution. The nitrogen in the molecule of ammonia has a lone pair of electrons and can act as a nucleophile, bonding to the partially positive carbon atom from a carbon-halogen bond. As the nitrogen forms this bond, the carbon-halogen bond breaks, with the bonding electrons going to the halogen, forming a halide ion. An intermediate is formed, with the nitrogen atom ending up with a positive charge as it has one too many bonds. Another ammonia molecule acts as a base and removes a H+ ion from the nitrogen and becomes a positively charged ammonium ion. When the nitrogen-hydrogen bond breaks, the bonding pair of electrons goes back to the nitrogen, making it neutral. This produces an amine product. An ammonium salt is also formed between the ammonium ion and halide ion released earlier in the reaction. This is more specifically referred to as an SN2 mechanism and occurs when primary and secondary halogenoalkanes react. For tertiary and some secondary halogenoalkanes, a different mechanism occurs, called an SN1 mechanism, where the carbon-halogen bond must break before the nitrogen can make a new bond to the carbon. Due to the positive inductive effect of alkyl groups, the nitrogen in the amine group is a stronger base than ammonia. If the concentration of ammonia in the reaction mixture is low, amines formed early in the reaction will act as a base and take H+ ions from intermediates formed later in the reaction and become alkyl ammonium ions. This can lead to the formation of alkyl ammonium halide salts. Amines are also able to act as nucleophiles themselves due to the nitrogen in the amine group having a lone pair of electrons. As a result, a primary amine produced earlier in the reaction can then go on to act as a nucleophile and react with any leftover halogenoalkane molecules, forming secondary amines. A secondary amine is then able to act as a nucleophile itself with any more leftover halogenoalkane molecules, and tertiary amines can be formed. If there is an excess of halogenoalkane, a tertiary amine is then able to undergo further substitution and form a quaternary alkyl ammonium ion, ultimately forming a quaternary alkyl ammonium halide salt as it pairs up with halide ions released by the halogenoalkane as it reacts. I hope you found this video useful. Please check out other relevant videos in the links given in the description below, and visit chemistrystudent.com for free notes and revision materials.